So the first thing that we're going to do today is go over the syllabus and all of that kind of good stuff. So it's posted on our Canvas page, so you can follow along with me if you want to or whatever. So I am Dr. Matthew Hartman. My office is across the street in Nefkin Hall. It's room 211. My office hours for this winter quarter are going to be Tuesday, Thursday, 9 a.m. to 2 p.m. So no office hours on Monday, Wednesday, Friday, because those days are just filled up with all the classes that I've got to teach. Um, let's see, emergency class disruption policy. In the event that a disaster or other emergency occurs, essentially the course is going to continue on Canvas and Zoom. Some of you may have noticed that I've already got a Zoom window open. I am recording my lectures and all of that kind of stuff. Um, I'm doing that as a courtesy. I am in no way, shape, or form required to do it, which means that I will post my videos whenever the hell I feel like it. Any person that comes up and asks me, when are you going to post that video? I guarantee that adds a day to when I get it put up there. So leave me the hell alone and let me do it on my own time since I'm being nice and doing it at all. All right, let's see. Course objectives. So at the end of this quarter, students should be able to apply basic circuit analysis techniques to steady state DC circuits, sinusoidal steady state AC circuits, and transient RL and RC circuits. You'll also become familiar with electrically equivalent circuits, complex power, and solving systems of equations in both the time and frequency domain. The official textbook for this class is Engineering Circuit Analysis, 10th edition by Height, Kemmerly, Phillips, and Durbin. Uh, Publisher and ISBN information is provided there. I hope none of you bought it. For what it's worth, it's not a bad textbook by any stretch of the imagination, but because you have access to all of my recorded lectures and all of that kind of good stuff, you don't really need a textbook. And if you really want to have a textbook, I provided a link in the introduction section of Canvas to a textbook called Circuit Analysis and Design by Ulabi, Maharbis, and First. Let me just open this link up real quick. So this is literally a free textbook that you can download. So you're not stealing anybody's intellectual property. I don't know if any of you actually care about anything like that. Some people do. But this book is being offered by the writers and publishers completely for free in a digital format. In my opinion, it is a pretty good book. So if you feel like you need a book, this is the one that I would actually recommend, and it won't cost you 200 damn dollars. Okay. Um, Going back over to the syllabus. Let's see. Disability disclosure stuff. If you need testing or classroom accommodations based on a disability, you need to be registered with the Louisiana Tech University Office of Testing and Disability Services. You should discuss those needs with me as soon as possible. If you do not have a current accommodation memo, visit the Office of Testing and Disability Services for assistance. And then that thing that's in blue there is a link that you can get to their website for and all that kind of good stuff. The class attendance policy is officially defined in University Policy 2206, which you can read at the link that I've provided. Attendance will be taken promptly at the beginning of class, and any student arriving after attendance has been checked without a reasonable excuse will be considered absent. Reasonable excuses do not include doctor's visits, car trouble, parking difficulties, oversleeping, or work schedules. So that is the official class attendance policy. The unofficial class attendance policy, which is the one that I actually adhere to, is that you're adults. And if you don't want to be here, that's fine by me. I'm going to get paid the same either way. I will say that students that show up tend to make better grades than students that don't. But if you feel that you're smarter than me and can survive in this class without my assistance, go nuts. Let's see. Then we're at the academic honor code bit. So in accordance with the academic honor code linked here, students pledge the following. Being a student of higher standards, you pledge to embody the principles of academic integrity. Then we get into the academic misconduct bit. There's a link for this in full here. But as far as the behavior, you are expected to maintain a, let's say, relatively professional classroom environment. I'm genuinely pretty laid back and all of that kind of stuff. So as long as people aren't, being wildly disrespectful or anything like that, we're all going to get along pretty okay. Um, don't be disruptive when I'm lecturing or anything like that. That pisses me off. But anyway, so just be a normal person. Don't be a dick to each other, and everything will be okay. As far as cheating goes, boy, it pisses me off a lot. So don't do it. Um, says here that collusion during examinations through verbal or electronic communication and or plagiarism of any kind throughout the course will result in a zero grade for the assignment or the exam, as well as a notification of the proper university officials. Multiple infractions will result in a zero grade for the course. So let's talk about this just very, very briefly here. Okay. I fully expect you guys to work together on homeworks and all of that kind of stuff. In fact, there are in-class assignments, which we'll talk about in a little bit, that is the purpose of that is for you guys to work together and develop a bit of a social network to help you guys figure some of this stuff out. With regard to the exams, I would actually love it if you cheated off of your neighbor because I make 4 different versions of the test, and the correct answers for version 1 show up on version 2 as wrong answers, which means if you copy off your neighbor, you're guaranteed to get a 0. So that would just make my damn day because I'm a vindictive jerk. So if you want to risk looking at your neighbor's paper and all of that kind of stuff while you take your test, have fun. I'll see you next quarter. So let's see. Homework. So homework is going to be handled on web work. There will be a web work assignment posted at the end of every lecture except for today's lecture. So the homework isn't going to kick off until Friday. You all will be granted unlimited attempts per problem. And the specific due date for each homework assignment is going to be listed on WebWork, but I'm going to talk briefly about how that's going to work as well. So the homework assignment that will be assigned on Friday is going to be due Tuesday at midnight. So effectively, whatever the next class meeting is, the day after that at midnight is when the homework is due. So if you, for the homework that's assigned on this upcoming Friday, if you complete that by Tuesday at midnight or 11:59 p.m. or whatever the hell time I have it set for, you will receive full credit. I will give you an additional 2 days to work on the problems for partial credit. Okay. So I know that that seems like a short window to receive full credit, and it kind of is because we're covering about 25 different topics in this class. And if you don't stay on top of the homework, you are going to be hopelessly lost. Okay. So that policy is to encourage you guys to stay as current as you can possibly be in this class. I have it set to be the day after our next class meeting so that once I get the tutoring sessions and all of that kind of stuff figured out, you will always be able to attend at least one tutoring session to get free assistance on your homework should you feel that you need it. It should be set up in a way also that I will always be available for at least one set of office hours before that homework is due so that you can come by and ask me as well. Okay. So there are multiple support structures to help you guys with your homeworks. I'll get the IEEE study night and the Ada Kappa Nu circuits tutoring times figured out probably later today. I'll send it out in an announcement on Canvas, and then when I come into class on Friday, I'll write them on the board so that everybody can see them and all of that kind of stuff. Okay. Let's see. In-class assignments. So after each lecture, including today's, a brief problem set is going to be distributed that will be worked during the remainder of the class meeting time as a group effort. Not saying you have to work with the people at your table, but you are encouraged to do so. These assignments are to be completed during the class period in which they are assigned and submitted digitally prior to the next class meeting, unless other arrangements are made with me. Okay. So again, I'm going to explain a little bit here. Okay. So the purpose of the in-class assignments is twofold. One, it's to help you all identify with what you didn't catch from the lecture before you have to go do the homeworks and all of that kind of stuff and get graded on it. The other purpose is that nobody wants to hear me talk about circuits for 2 hours straight, 3 days a week. So this is a way to get you guys some practice where I only talk about circuits for maybe 75 minutes a day for 3 days a week. So this gives you a little bit of time not listening to me rant about dumb shit. Okay. These assignments are not graded for completeness and they are not graded for correctness. They are just a participation grade. So if you only get one part of one problem done by the end of our class meeting, then turn that in and you will receive 100%. If, however, you are screwing around on your phone, watching soccer, playing dumb mobile games and stuff like that, I don't care how much of it you get done, you're going to receive a zero because this is class participation, not screw around on your phone time. Great. Okay. So anyway, they are due at the beginning of the following class, and they are all expected to be submitted digitally. So just to show you guys here, if we go over to our course Canvas page, there's already a place that you guys could submit in-class assignment number one. And if we look at this, let me see what happens if I click on it. It's due on Friday at 8 a.m., which is the beginning of class, and it closes, meaning that you cannot turn anything in after 8:05 a.m. on Friday. So there is a 5-minute grace period for students that forgot to turn it in before the beginning of the next class to get it turned in. And if you can't get it turned in by 8:05, you get a zero. It is class participation, so there's really no reason you shouldn't have it turned in by the time you leave this room today. So I just want to be clear about that. So you get an extra 2 days to sort stuff out if you want it or need it, but it's not remotely necessary because, again, this is just a participation grade. You don't have to get it finished. You don't even have to get it right. You just have to try, and you will get 5% of your final grade for literally just trying. All right, going back to the syllabus. There will be 8 mini laboratory sessions that were given throughout this quarter. The first of these mini labs will be on Friday, so 2 days from today. The labs are expected to be completed in groups of 2 to 4 students. It's not going to hurt my feelings if it's 5 students or whatever. If there just happens to be 5 of you guys at a table, 6 is kind of stretching it. Completion of the mini lab assignments will typically require the use of a Windows laptop and a digital multimeter. With regards to the multimeters, there is a bin of multimeters over on that side of the room that you guys are welcome to use. I will tell you that roughly 90% of the fuses are blown in those multimeters. So if you have to make any sort of current measurement, it's probably best if you bring your multimeter yourself, like your own multimeter that you got from the 120 series and all of that kind of good stuff. There is a kit with this class. It costs a whopping $10, and not every student needs to buy one. Realistically, if you have one, maybe 2 per table, if your table has 6 folks, that's plenty. So if everybody at a table of 4 wants to chip in $2.50, that's fine. If you want to decide, let's say you aren't allowed to drop the class because you bought the kit, so you have to bring it for everybody for the entire quarter. If you want to do that, go nuts. But you will need to get your hands on this kit before class on this upcoming Friday because we are having our first lab on Friday. So I've made you aware of it. Let's see. Exams. There are 3 exams that are given during the duration of the course. All exams are closed book and closed notes. I will provide you with an equation sheet for exam 3 and exam 3 only. So that means for exam 1 and exam 2, I'm expecting you to know all of the equations and all of that kind of stuff that I'm going to be presenting you over the next several lectures. Okay. Let's see. Only FE approved calculators are permitted for usage during the exam, and then you can find a list of FE approved calculators at that particular link. For what it's worth, and I am not paid to say this in any way, shape, or form, but at some point TI should start shelling out money for me. The TI 36X is my favorite calculator for this class. If anybody has one, that's great. If you have the TI 30X, you need to upgrade from that peasant calculator quick, fast, and in a hurry. You are going to get wrecked in this class if you have a TI 30X, just being bluntly honest. Okay, so this is my favorite calculator. The reason why it's my favorite calculator is because it can do math using complex numbers very, very well and very, very easily. Um, my second favorite calculator is probably this guy right here. This is the Casio 115, just a regular workhorse calculator. Has the exact same functionality as the TI 36X. The reason why it's my number two calculator is because in order to do complex math, you have to switch it into complex mode, and that makes it behave differently. The TIs just work. This guy has different modes to do different things, and I find it annoying to have to switch back and forth between the modes, so it gets a demotion. This Casio 991 is also a really good calculator. It is the only calculator that is FE approved that can solve a system of four equations and four unknowns. This particular model, which is the one that I prefer out of the 991s, has actually been discontinued. So if you're buying one from a friend here on campus, it's probably pretty okay. But if you're buying one off of eBay or some such nonsense, I'd be willing to bet that it's a counterfeit. I've had students accidentally buy counterfeit calculators before, and whenever you put stuff in, it just constantly gives you math errors and stuff like that. So be very, very wary if you're going to buy this powerful calculator because Casio no longer makes it. So you might be buying a knockoff piece of crap that doesn't actually work and pretty much guarantee whatever scammer sold you this calculator isn't going to give you a refund. Okay. So make sure you're buying a real Casio if you're getting one of these. They do have an updated version of the 991 that looks like this. I find it significantly more difficult to use. Just the way that it's laid out confuses the hell out of me. So if you have one of these and you know how to use it, that's awesome. I haven't really figured out how to use it super well yet. So I can't help you on this one nearly as much. For those of you that use HP calculators, there are two HP calculators that are FE approved. I don't understand that witchcraft at all. Or excuse me, not Casio, HP calculators use a different order of operations that makes no sense to me whatsoever. So I haven't even bothered buying one of those because I know that I'm not going to ever take the time to actually learn how to use it. So anyway, there's my rant about calculators. Like I said, the TI-36X is the GOAT for this class, but the 115 is a very close runner-up. All right, let's see here. Grading. Okay. So here's how grades are weighted in this class. So your web work, which I already heard some of you complaining about earlier in class, it's totally fine. I agree. It's a miserable experience. It is worth 15% of your grade. Okay. And then we have the in-class assignments. That is 5% of your grade. The mini labs are another 5% of your grade. And then we have exam one, exam two, and exam three are all worth 30%. And then there's that little fancy symbol there that's leading me to this footnote that says the weight of the exam on which you receive your lowest score will be reduced to 15%. So that essentially means that you can have one bad test day and still make an A in this class. As long as you make higher than a 34 and you do all of the other work, an A is still possible. If you have two bad test days, I think you all know it, but you should probably drop. Okay. So if you just crash and burn on the first exam, which for what it's worth, in my opinion, exam one is the hardest exam in this class by far. So if you do very, very poorly on exam one, which a lot of students do, wait until exam two before you figure out whether or not you actually need to drop, because chances are exam one is the one that's going to be weighted the least for all of you. Typically speaking, the average score on exam one is usually somewhere in the low 60s to mid 60s. The average score on exam two is usually somewhere in the mid 70s to upper 70s. Okay. So exam one is genuinely difficult. So don't let that be the thing that tells you whether or not you should drop the class. It literally gets significantly easier as soon as we finish this stuff up. Okay. Let's see. All of the homework assignments, in-class assignments, and mini labs are weighted equally. So that means for your homework assignment, it doesn't matter if it has 7 problems or 3 problems, it still counts the same amount towards your final grade and all of that kind of good stuff. Um, for what it's worth on the exams, they are out of 105 points, but I grade them out of 100, meaning that there's 5 bonus points, or let me rephrase that, at least 5 bonus points built into every single one of the exams. Um, so there's a little bonus built in there. Because this is an ABET year, we are being asked to collect all of the student work. So there's going to be a place on Canvas that you guys can submit your actual written out work for all of your web work assignments and stuff like that. Turning all of those in will net you 2% bonus towards your final grade. So that's 2% just tacked onto the end if you simply turn in the work that you did when you were working the homework assignments anyway. Okay. So I would obviously highly encourage all of you to do that. So the grading scale for this class is a traditional 10-point scale. Um, Notice I have on here that an 89.99 is a B. Yes, I am that much of an asshole. So if you want to earn an A in this class, you need a 90.00 or higher to get it. I do not round. I also don't curve or anything like that. So if you want to make an A, earn your A. The last date that a student can drop a class or resign his or her entire schedule with a W grade for winter 2026 is Friday, February 6th. That will be after your second exam has been given and graded. I don't expect the contents of the syllabus to change, but if I need to change them, I reserve the right to do so as long as I let you all know. And then we have boilerplate information about the emergency notification system, sign up so that you know if classes get canceled or moved online because of a weather event. Here is, I don't even know if this is officially the university COVID-19 policy anymore, or it's just mine, but essentially, if you're sick, don't show up and get me sick. That pisses me off. So we have Zoom and all of that kind of good stuff so that you can attend class virtually. So do that if you're ill. Counseling services are available to you at no cost. Visit the counseling services website to learn more. Then we have the official university non-discrimination policy. If you feel that you're being discriminated against um, due to your race, color, national origin, religion, age, sex, sexual orientation, marital status, or disability, contact Ms. Mortissa Harvey, the Director of Title IX Compliance. Section 504 is a federal law designed to protect the rights of individuals with disabilities in programs and activities that receive federal financial assistance from the U.S. Department of Education. If you're concerned about 504 compliance, contact Annie Jantz at the Division of Student Affairs, and I've provided her contact info as well. And then if you have any issues with Canvas or Workday, please direct your questions or problems to the Computing Center Help Desk. There's a link there, and then there's also the email address as well as the phone number. And then finally, we have our tentative course schedule, which tells you what topics are going to be covered on every day, which web work assignment goes along with those topics, the mini labs, when they are, the topic of the mini lab, and all of that kind of good stuff. You'll see here that all of the exams are currently scheduled. So your first exam is going to be the Monday evening after we get back from the Christmas holidays. So you've got a full week to remember how to circuits after we get back before you take your first test. It is a night exam. All 3 sections will be in the same place. I believe I have reserved ISB 318, so that's the large chemistry lecture hall upstairs in this building for us. If you have extended time accommodations, you will take your exam at 6 p.m. as well. It will just be in a different room, and you will have until 9 p.m. to finish it. So you have 2 hours for the test if you're a standard time student, 3 hours for the exams if you're an extended time student. Any questions about the syllabus and all of that kind of good stuff? All right, so hopefully you have all gained from my exposition on the syllabus that I am an asshole, but I'm a fair asshole. Yes.
To attend class through Zoom? Do you have to notify you or?
Nope, just log on to the Zoom thing. Yeah. For what it's worth, when I take roll, if you're on Zoom, I don't care. Meaning, like if you're not physically here, I don't add you to the actual roll sheet. But because that doesn't mean anything, it doesn't mean anything. So you can still turn in your in-class assignments and all of that kind of good stuff. If you have to miss a class and you happen to miss a mini lab, the last class meeting of the entire quarter is dedicated to allowing students to make up those mini labs. So there's literally no part of your grade that you will miss by being unable to physically attend a class. Okay. Any other questions? All right, so let's get into the lecture. This crap out of the way. So these first few class meetings that we're going to have are going to kind of be a review. There will be some new topics that are kind of introduced alongside some stuff that you learned in the Engineering 120 series. But we're going to cover damn near everything that you covered in the freshman series in the first 4 days of this class. Okay. Then after that will be new and arguably exciting things. Okay. So this first class meeting is dedicated to discussing basic circuits terminology so that we're all talking the same language when we are discussing circuits. Okay. So the first thing that we are going to discuss is the concepts of networks, nodes, and connections. So I'm going to start by introducing a generic circuit element. Okay. So I'm going to put a box here. And I'm going to label this box with the letter A. So I'm going to refer to this as circuit element A. Okay. And this is going to be a two-terminal circuit element. So I've drawn one terminal on the top and another terminal down here at the bottom. And these terminals are what allows me to make connections to other elements directly or to wires and things like that. Okay. So this two-terminal element could be any number of different things, right? We could use this generic circuit element to represent a resistor, a capacitor, an inductor, a diode, a battery, a voltage source, a current source, lots and lots of different things, okay? The overwhelming majority of the circuit elements that we are going to deal with in this class are two-terminal elements. It's not until we get to op amps, which is actually an eight-terminal element, that we're going to see anything that isn't a two-terminal element. But you guys have worked with three-terminal elements before. Can anybody remember a three-terminal element you worked with in your prior classes? Transistors, right? So a transistor, a MOSFET is usually either a three-terminal element or it can be thought of as a four-terminal element if you're doing integrated circuit design, which we're not going to be in here. So that's a pretty common example of a three-terminal circuit element. An electrical transformer is a four-terminal circuit element, sometimes five-terminal if the secondary has a wiretap on it. But anyway, the terminals are just where we make connections to other elements. Okay. So I'm going to add another generic circuit element here. This will be B, and I'm going to connect one terminal of element B to one terminal of element A, and then I'm going to have the other terminal sitting over here open like so. Okay. So whenever two or more circuit elements are connected together, they form what we're going to call a network. So I am just going to officially define that a network is an interconnection between two or more circuit elements. Okay. And we are going to define now a node as a point of interconnection between two or more circuit elements. So this small network that we have right here actually contains three nodes, okay? So we've got this node right here, okay? So this is where we can make an interconnection to another circuit element, so it is a node. We've got this node right here where elements A and B are connected to each other. And then we've got this node right here, which is this open terminal of element B where we could make a connection to another element as well, okay? So when we add more circuit elements, which I'm about to do, sometimes it might get a little bit more difficult for us to figure out where our nodes are and things like that. So I'm going to show you guys some helpful hints, okay? So I'm going to add a circuit element C like so. And then I'm going to connect A and C together with this line representing a wire. I'm going to have circuit element D over here out to the right. And I'm going to connect D to B and C with a wire and D to C and A on the other side with a wire like so. Okay. So our network has gotten a little bit more complicated, and it is not as easy for us to determine how many nodes we have or anything like that. So what I'm going to do is I'm going to show you how I tend to identify my nodes, okay? So what I do is I start at one of the circuit elements, and then I just follow the terminal and any attached wires until I hit another circuit element. And I just need to make sure that I take into account all of the different kind of paths and connections that we could have. So this thing that I've done here in the top left would constitute one node. Now let's look at what's going on if we leave element B on the right-hand side. So I hit this branch here, so I can go down and hit element C, or I can continue on to the right until I hit element D, and this whole thing forms another node. And then lastly, going from the bottom of element A, go down to the right. Now I hit this branching path, so I'm going to go up and touch element C, and then over to the right and up to touch element D. And so we can see that there are three nodes in this system. So I'm just going to label this guy as node 1, this guy is node 2, and this guy is node 3. In our class meeting on Monday, we are going to more formally explain why the wires essentially become a part of the node in this class. Okay, so the wires that we use to connect circuit elements together are going to be treated as just part of that larger node. Okay, so before I move on from this, does anybody have any questions about how I identified these nodes in this particular network? All right, hopefully fairly straightforward. Okay, so let's take a look at a couple of things. So if we look at circuit elements A and B, or particularly the node that I have labeled as node 1, we have these two elements, excuse me, that are connected together, and there are no branching paths, right? So there is a single path to go from A to B through this node that I've labeled in red, At no point does it branch off and try to touch any other elements. So that is an example of what we're going to call a series connection. Okay. So a series connection is going to be a connection between two. I'm going to underline that because for right now, with our current level of understanding, a series connection is only going to encapsulate exactly two circuit elements at most. As we learn more, we will adapt this definition. Okay. So it is a connection between two circuit elements with no additional branching paths. So as I mentioned a moment ago, elements A and B would be considered to be connected together in series because node one satisfies the definition of a series connection. Okay. Now let's look at elements C and D. Okay. So in elements C and D, their top terminals are connected together at the blue node, and their bottom terminals are connected together at the green node or node 3, right? So this is an example of a parallel connection where I'm going to define a parallel connection as a connection between two or more circuit elements where all sets of terminal pairs are shared. Okay. I tried to make that incredibly generic because it's technically possible to connect three terminal elements together in parallel and all of that kind of good stuff. It just all of the terminals need to be shared, right? So C and D here are shared because they're touching the same node uh, on the blue node and the green node at the bottom. So this is what makes a parallel connection. One of the reasons why I really like using different colors to identify my nodes is because if I can see that two elements touch the same two colors, I automatically know that they're in parallel. I don't have to have any thought. It doesn't matter how they're physically oriented in my network or circuit or anything like that. If they're both touching blue and they're both touching green, they are in parallel as long as I use different colors for every node. Okay. So now I'm going to hit you guys with a trick question. Okay. How would you describe the connection between element B and element C? So they're not in series because B and C have a branching path that goes off to touch element D. Okay. So can't be a series connection based on our current understanding. And it wouldn't be a series connection based on our later understanding either. They're just not in series. Okay. Are they in parallel? No, because while they do share the blue node, element B is touching red and blue, and element C is touching green and blue. And I guess maybe I should have used different colors because if somebody is red-green colorblind, they might see both of those as gray and they erroneously think that they are in parallel, but that wasn't my intention. So, um, isn't in series and isn't in parallel. That's perfectly okay. That's one of the things that kind of annoys me a little bit about the 120 series is I don't think there's enough attention paid to the fact that it doesn't have to be series and it doesn't have to be parallel. It can be none of the above, and that's perfectly okay. What we're going to do as we progress in this class is learn tips and tricks and techniques once we get to dealing with specific circuit elements in order to make combinations that aren't in series or aren't in parallel look like they're in series and parallel to make the math easier. Okay, but that's something for a little bit further down the road. All right. So I want us to work an example together. So I'm just going to switch to a second page here, and I'm going to draw another network. Okay. So this one's going to be a little bit more complicated. So here I've got a generic circuit element A connected to a generic circuit element B, like so. Here's a generic circuit element C down here at the bottom. Here's D. E, F, G, and lastly over here will be H. Okay. So this network contains 8 different generic circuit elements, and I want us to answer the following questions. So A, I want to know how many nodes does this network contain? Okay. And I'll give you guys a few moments to try to sort that out, and then we'll work on the answer together in a little bit. Anybody, excuse me, anybody got an answer for me? Adam. I also got 5. So we have this node here at the top left, this node here at the bottom left. We've got this node here at kind of the top middle. This node here at the top right. And lastly, actually, let me use that paint color. This node here at the bottom. Okay. So counting these guys up, I'm going to call this guy node 1, 2, 3, 4, and 5. So there were 5 nodes. Good job, Adam. Hopefully everybody else got 5 and we're just too intimidated by my pink shirt to say anything. I don't know. All right. The second question I want to ask you guys is which of the elements actually, which of the element pairs are connected in series? So do we have any nodes that don't contain any branching paths? Which ones? Node one and node four, right? So since node one is where A and B are connected, then that means that A and B must be in series. And since node four is where A and C are connected, then that means A and C are connected in series, okay? Once we learn a little bit more about a thing called Kirchhoff's current law, we'll be able to more formally say that A, B, and C are all in series, but we're not there just yet. So I'm just going to leave this alone and leave it in pairs like so. Okay. And then lastly, I want to know which of the elements are connected in parallel. Yes, Matthew. F, G, and H. Absolutely right. Okay. There any more? E and D. Okay. So E and D is not correct because while they do share the green node, E is also connected to the purple node at the top right, while D is connected to the pink node on the bottom. So they're not sharing both sets of terminals, so they're not in parallel. So F, G, and H is the only correct answer because they all share purple on top and they all share pink on bottom. All right. So before we move on from networks, nodes, and connections, does anybody have any questions or anything like that? All right. So I'm going to jump back over to the previous page. And now we're going to start talking about circuits, loops, and meshes. So I'm going to redraw our network from before. So here's element A connected in series to element B. Here's element C, which was connected in parallel to element D, like so. This is just the exact same network that we had previously. I just redrew it because I colored all over the last one. So whenever a network contains at least one closed path, we're going to talk about the definition of a closed path here in a minute, then the network may be considered a circuit. And each of those closed paths is referred to as a loop. Okay. So let's define a circuit as any network that contains at least one closed path So if you remember back to the beginning of the lecture where I only had A connected to B, that was a network, but it wasn't a circuit because it wasn't closed, right? Now that I've got C and D in this path along the bottom, that's what's making this a circuit, okay? And we're going to say that a loop is any closed combination of circuit elements and nodes. So I'm going to ask you guys what is kind of a trick question. How many loops does this circuit contain? Three. Okay. So I also agree that the answer is three. But I would be willing to venture a guess that there's at least one or two people in here that don't understand why the answer is three. So I want to explain things. Okay. So when I'm identifying a loop, I'm going to choose a starting place, right? So I'm going to choose the bottom left-hand corner of this circuit. Okay. I'm going to go up through element A, keep on going, turn around to the right, go through element B, keep on going. And now I have a choice. Well, I'm just going to arbitrarily choose to go down here through element C, and then I'm going to come back this way like so. So this is one loop that I'd be willing to bet everybody saw. And I could do something pretty similar here around this path, right? So I could go up through C, across through this node, down through element D, and then back across through this bottom node. And that gives me my second loop. The third one, which is less obvious, but it is still a loop. If I start here and I go up through A, across through B, now instead of turning down to go through C, I'm going to go across and then down through D and then back across like so. So this one in green is my third possible loop. So around the perimeter of the circuit, essentially. Okay. So these are the only three possibilities. So if I went just for the hell of it, I'm going to show you one that doesn't make sense just for demonstration purposes. And I'm going to do this kind of sloppily. Okay. So if I start here and I go across, go through here, and then I come this way and go back around, that isn't a loop because it's two loops because it's closed twice, right? So I have this one pathway and this other pathway that forms two separate loops. So I can't cross over the loop without closing it. Okay. So that's why it isn't an additional loop. Okay. So now what I'm going to do is I'm going to define what's called a mesh. Okay. And a mesh is simply any loop in a circuit that does not contain a smaller loop. So which of the three loops that we've identified would be considered a mesh? So three is the only one that isn't a mesh because it contains the two smaller ones, right? So essentially, when we're looking at a circuit, if we see window panes and stuff like that, those are always going to be our meshes. It's the smallest closed path that we can form that doesn't have another path inside of it. This third loop follows mesh one and then follows mesh two until it closes up. So it contains both of those two smaller loops. Does that make sense? Okay. So to hammer this home, this will be the last thing that we're going to talk about today. So it looks like we're going to get out quite a bit early, although you do have an in-class assignment to do. So I'm going to go back to our example and I'm going to redraw this. Now I'm going to call it a circuit since we know that it's a circuit. And we're going to figure out how many meshes and loops are in this guy. Okay. So here's A, B, C, D, E, F G, bless you, and H. All right. So here's my hastily drawn circuit. So I'm going to ask for how many meshes there are first. Somebody has already responded 4, and they are correct. So just to help identify them for you all. I've got this mesh. I've got this triangular mesh. Let's call that guy 2. I've got this other triangular mesh. And then lastly, I've got this guy over here on the right. So the last thing that I want to ask you all is how many loops does this network contain?
Well,
10. And we're going to approach this formulaically, okay? So somebody said 5, and if we just look at the previous example, I kind of see where the 5 came from, right? So we have the 4 meshes, and then we have one loop around the outside, so that makes 5. But there are other closed loops that we can form that we need to think about, okay? So I'm going to break this down into different things, right? So I'm going to say single mesh loops. These are literally just our meshes. We already know that there are 4 of them, okay? But now we could talk about 2 mesh loops. So what loops could we make by combining only 2 meshes, okay? So that might be something like this guy, right? That is a closed path that encapsulates meshes 1 and 2. But we also have, I guess I'll do this gray color. This gray closed path right here, so it's starting and ending at the same node, also encapsulates 2 meshes because it encloses 2 and 3. And then it should be fairly obvious that there's another one that we could draw that encapsulates 3 and 4 as well, right? So that would be this guy right here. So there are a total of 3 2 mesh loops. There are also some 3 mesh loops that we could get. So just so that this doesn't get too aggressively busy, I'm going to erase some of this stuff. So a three mesh loop might be this loop right here. You guys can see that where it encapsulates one, two, and three. So what's my other three mesh loop going to be? Two, three, and four. Yeah, the one on the right hand side. So we had exactly two three mesh loops. And then lastly, we have our four mesh loops. There's only going to be one of those. That's us drawing the path that just goes around the outside of the circuit. So realistically, it's never really super important that we're able to identify the number of total loops after today. Okay. That being said, when we are going to be doing things like applying Kirchhoff's voltage law and stuff like that, having a good understanding of what constitutes a loop or what constitutes a closed path is a good thing to know because it gives us lots of options for how we choose to apply those circuit analysis techniques that may avoid some places where we don't have enough information to do anything with it. Okay. So I'm never going to make you count these again after today, but understanding that there are lots of different ways that we can get from point A to somewhere else in the circuit and back is actually very important for how we're going to be doing some analysis a bit later on. All right, so I don't have anything else that I particularly want to talk about for today. I'm happy to answer any questions that you all may have. Feel free to come up here to the front and grab your in-class assignment. As soon as you finish it up, you're free to get out of here.